In this video, we present our research on learning to control camera exposure via deep reinforcement learning. To begin with, what is camera exposure? Exposure refers to the amount of light that reaches the image sensors. In the camera imaging pipeline, this light passes through several stages including pre-camera elements like the lens filter, shutter, and aperture, which can introduce various effects such as motion blur and defocus blur. The sensor with a color filter array then captures the light, followed by processes like gain control, a deconversion, and in-camera operations such as white balance, demosaic, sharpening, and gamma correction. Exposure control in cameras involves adjusting factors like aperture, exposure time, and gain to produce the desired exposure for a photograph. This control is critical in ensuring well-exposed images, whether for aesthetic purposes or practical applications like robot vision. Proper exposure control helps manage dynamic lighting conditions, reduces image noise, and minimizes issues like flickering and motion blur. For robotics, exposure control is vital for real-time vision tasks. Robots need to adapt quickly to changes in lighting to maintain optimal vision performance. However, challenges include the ambiguity of what constitutes a desired image for robot vision and the need for real-time processing on embedded systems. Given a scene's radiance, finding the optimal exposure parameters involves balancing several competing factors. To address these challenges, we introduce a method using deep reinforcement learning for rapid exposure control. Our approach, DRLAE, is the first to use DRL for auto exposure control, achieving rapid adjustment within 3 to 5 frames and real-time processing on a standard CPU device. This method outperforms traditional auto exposure systems, especially in dynamic real-world environments. For training the DRL model, we designed a light-controlled darkroom to simulate diverse and dynamic lighting conditions, ranging from strong to dim lighting. This controlled environment helps in training the model effectively while minimizing the simulation to real gap. We also use spatial domain randomization to alleviate restrictions on objects and backgrounds during training. Our model uses vectorized intensity history for state representation, which is lightweight and reduces computational complexity compared to traditional CNN features. For action, we adopt a relative and continuous action space, which allows for more stable convergence and minimizes flickering issues compared to discrete action spaces. The reward function is designed to be flicker-aware and image attribute-aware, ensuring moderate image brightness and smooth exposure transitions. We use the soft actor-critic algorithm for training due to its sample efficiency and effectiveness in our limited training environment. Our method achieves rapid convergence and superior performance in real-world scenarios. We conducted zero-shot real-world verification in various environments to compare our DRLAE method with the built-in auto exposure. In indoor environments with dramatic lighting changes, our method demonstrated rapid convergence speed within 5 frames. In outdoor environments with a moving vehicle, our method captured well-exposed images consistently and achieved real-time processing on a CPU device. Furthermore, our method detected 38% more SIFT features on average. Our method also captured objects 3 to 4 frames earlier than the built-in auto exposure, and show fewer steps to converge in a simulated dataset environment. It is also possible to focus on the part of the given image, that is ROI-aware exposure control, which can be combined with the user input or detection result. In conclusion, our DRLAE method addresses key challenges in exposure control for robot vision, providing rapid and stable exposure adjustments in real time. Thank you for your attention.